started. Today we're joined by Jeff Neasham from Newcastle University. Jeff joined the university as a research associate, where he's involved in research and commercial product development in underwater acoustic communication, sonar imaging, and wireless sensor networks. He's currently a senior lecturer in communications and signal processing at the School of Electrical and Electronic Engineering. His work on underwater acoustic design has been commercialized by 3 UK companies, and I'll add our Daisy and Microphone teams at PMEC are using one of his products, the nano modem, and have been very pleased with it. Jeff's going to join us to tell about some of the challenges posed by underwater acoustic communication channels and about the design of cost-effective underwater acoustic communication devices. And with that, I'll pass it over to Jeff. Thank you. Welcome.
Okay, good morning, everyone. It's Friday evening here, but as I was just explaining, it's not really spoiling anything because most things are locked down currently in Newcastle. Okay, so I'll go through what I'm going to be discussing. So I'm going to give you a little bit of background on our acoustics at Newcastle and the history. Then I'm going to give some background theory on underwater acoustics and particularly the channel properties for those of you who won't be particularly familiar with that. Then I'm going to talk about spread spectrum technology, which is one of the key technologies we use to overcome these difficult channel effects. Then talk about how we've managed to engineer this spread spectrum technology into ultra low cost devices, so very small devices, very low cost devices, and very low power devices. And then talk about some of the projects where we're currently applying this technology in underwater sensor networks. And as the title of my presentation said, we're really trying to enable the Internet of Underwater Things, so networks of large numbers of small, low-cost devices, allowing us a large coverage of the environment. So I'll talk about things like marine mammal detection using these devices, vessel detection, and some projects we're involved in on locating lost fishing gear. Although hopefully you'll see that the applications for this technology are very wide and varied. So just to talk about our team here in Newcastle, we're a small team of about 3 academic staff, 3 or 4 permanent research staff, and typically between 3 and 6 PhD students at any one time. And we have more than 25 years experience in acoustic signal processing, most of that applied to underwater communication and navigation, although we do work on sonar imaging and passive acoustic detection as well, as you'll see later. So we've got and we work on these systems right the way through from the fundamental waveform design and development of signal processing algorithms, right the way through to the transducer design and the hardware implementation. And a strong feature of our work has been commercialization. So we tend to take our technologies to quite high TRL levels and then work with companies to turn them into commercial products. And I'll talk about 1 or 2 examples of our commercial products in a moment. In terms of facilities, so we're very well equipped for this kind of underwater acoustics work in Newcastle. So in our lab, we have a custom-built anechoic test tank, which is lined out with special tiles to absorb sound. That allows us to simulate being a much bigger volume of water inside our relatively small tank. So that's a very useful facility. We have a number of ROVs that we use as test beds, lots of different acoustic transducers and instrumentation that we use. We have access to that's berthed just a few miles from Newcastle, and that gets us out in the North Sea to do our experimental work. And we also have now a permanently installed offshore acoustic data buoy. So just to give you an example of the technologies that we've taken through right the way from first principles in research right the way through to commercial products. So C-Track is an underwater acoustic modem and ultra short baseline positioning system. It's a small miniature unit. It's about 160 millimeters high. It's suitable for mounting on small ROVs and even divers. And there are around about 1,000 to 1,500 of these operating around the world right now. Most of them tracking underwater vehicles, but quite a few for other applications. And this allows you to exchange data at ranges up to 2 kilometers, a couple of different data rates. It allows you very accurate ranging with a resolution of about 10 centimeters, and allows you to measure direction of arrival with an accuracy of about 2 degrees. So with that, you're able to calculate X, Y, and Z position on an underwater device, and so hence it's commonly used for tracking underwater vehicles and divers. It's also been integrated into a diver navigation console known as Artemis, which you see here. And there are an increasing number of these devices being used by all kinds of divers, from MOD in the UK, defence divers, through to even recreational divers are buying some of the cheaper systems. So this is a case where we took our technology up to quite a high TRL level. Then we worked with this company Blueprint Subsea to design the final product, and we still help them with the testing and support of this product. So talk about underwater acoustic technology. So as hopefully some of you realize, that electromagnetic waves are very severely attenuated in water, especially seawater, due to the high conductivity. And for that reason, the whole world of radio communications that we know and love is not really any use to us underwater. However, sound waves travel with much lower attenuation, and that forms the basis of most underwater communication and positioning technology. So nature's way ahead of us. Obviously, they use dolphins and whales use sound signals quite commonly for communication and navigation. And we're able to design systems that do exactly the same thing. And sometimes some of our ideas have inspiration from nature. But the downside to acoustic signals is that although they'll travel a lot further, the propagation is quite complex, and this leads to typically far more difficult channel conditions than in wired or radio communications. So all of the problems we're up against in reliable radio communications, they tend to be amplified in magnitude in underwater acoustic communications. So I'm going to talk through briefly what these challenges are. So the first one is that we have very little bandwidth to play with typically in the underwater acoustic channel. So the absorption processes for sound in the sea are highly frequency dependent. That means our transmission loss increases rapidly with frequency. So if we compare attenuations at, say, a frequency of 15 kilohertz compared to a frequency of about 50 kilohertz, then we've got about 21 dBs different, which means we've got to transmit 100 times as much power to get the same distance at 50 kilohertz compared to 15 kilohertz. And also this steep gradient here limits the bandwidth we have available. And in any communication system, bandwidth is the ultimate thing that dictates how fast we can send data. The other big challenge, and this is possibly the biggest one, is multipath propagation. So if we have our acoustic signal traveling from a device to another device, and our emission is omnidirectional and we're sending sound in all directions, then as well as a direct path from A to B, we're also going to get reflections from the sea surface and the sea bed. And here we're just showing a simple case with 2 reflections. In reality, we get multiple reflections going back and forwards between the sea surface and the seabed. So for that reason, the signal that arrives at the other end is a whole mixture of paths delayed with respect to each other. And this leads to what we call intersymbol interference, which is interference between the current data we're trying to transmit and the previous data that we send. Viewed in the frequency domain, we view this as frequency selective fading. So we get either constructive or destructive interference between these signals at different frequencies. So narrowband signals can actually completely fade out under these conditions due to destructive interference. And the time spread, the time between the first arrival and the last arrival, can span hundreds of our data symbols. So this is a very, very severe problem. And if we don't deal with it, our data communication will be very unreliable. As well as that, our multipath channel is highly time variable. So this is showing an impulse response. This is the result you would get if you sent a very short burst of energy through the water. And this is what we would receive. And you see we have a first path that arrives, and then we have a whole series of different reflected paths. And as you can see, these signals are fluctuating wildly in amplitude. And you'll see signals appear from nowhere and then fade out again. And this is pretty common. And this is a measurement taken in real time. We're measuring the channel every 50 milliseconds and playing back the result. And it shows how dynamic our channel is. The consequence of this is that anything we do to try and compensate for this multipath problem has to be done in a very closed loop fashion, because literally by the time we've measured the channel, it has changed. So it's not just a case of setting up, measuring the channel, setting things up and running like that all day, because literally nothing stays constant for more than a few tens of milliseconds in this channel. The next challenge is Doppler effects. Now, because sound velocity is very low, our platform motions are actually a significant proportion of the wave velocity. So sound velocity is about 200,000 times slower than the speed of light, the speed of electromagnetic waves. And so our Doppler effects are a lot more severe. And actually, if you calculate the Doppler effect on two supersonic aircraft flying away from each other, if they're transmitting a radio signal between them, that's still many orders of magnitude smaller than the Doppler effect that we get from a small vehicle chugging along at a few knots velocity. So Doppler effect's a big problem for us. And the reason it's such a problem is that it affects the synchronization of our signals. So for those of you not familiar with the Doppler effects, this is the compression or expansion of a waveform in time due to the relative motion. So if we're moving towards our source, if our source is moving towards the receiver, then what the receiver picks up will appear to be shifted up in frequency or compressed in time. And that's a more complete description for a broadband signal. Likewise, if it's moving away, then it will be stretched out in time. But this affects the synchronization process for communication. So we have a sampling clock that assumes a certain timing on the signal arriving, and the Doppler effect means that what we receive is not exactly what we transmitted in terms of the time frame. So we also have to compensate for the Doppler effect and maintain synchronization. And this can be a very challenging thing to do. And again, the Doppler effect's not constant because of this random motion in the channel and potentially quite complex motion of our platforms. Then the final challenge, as in most communications, is background noise. We're not just going to pick up our transmitted signal, we're going to pick up signals from all sorts of other sources. And acoustic noise in the oceans originates from shipping, from propulsion system noise, from surface waves, wind and rain, the effects of weather on the sea surface, biological sources, including the cetaceans that I talked about earlier, but also even things like Crustaceans, clicking shrimp can be a source of a lot of noise in some environments. And also other man-made acoustic signals, other acoustic systems like sonars, for example. So they're all going to contribute to the background noise that we've got to work against in our communication link. Now, a typical ambient noise spectrum in the middle of the ocean peaks at about 1 kilohertz and it rolls off at about 20 decibels per decade. So for each time frequency increases by a factor of 10, our power level decreases by about a factor of 100. And that's typically what we'll hear out in open oceans. But obviously, if we've got dominant noise sources nearby, it can look quite a bit different from that. So it very much depends on the environment and what other activities there are in the area. But an interesting thing is that if we go back to our problem of transmission loss or sound absorption, you see, although sound absorption favors low frequencies, because our noise is rolling off in the other direction, for any particular range, you tend to have an optimum frequency where you'll get the best signal to noise ratio. So you've got one curve going this way, another curve going that way, and so there's an optimum there at the bottom, and that will vary depending on the range. So for example, for a range of about 5 kilometers, the optimum frequency to be at from a point of view of signal to noise ratio is about 10 kilohertz. So these are the fundamental challenges we're up against. And I'm now going to talk about the techniques we use to try and overcome these problems. So spread spectrum is something that we use extensively in our research and in our products. And the idea of spread spectrum is that we can trade off bandwidth for immunity to the channel effects. So if we start with a relatively narrow band information bearing spectrum, so we're transmitting a relatively low data rate, and then we transform that low bandwidth signal into a broad bandwidth signal. And this is the process that we call spreading. And I'll talk in a moment about how we actually achieve that. But we're transforming a narrowband signal where all the energy is concentrated into a narrowband into a broadband signal where the energy is spread across a much wider band. And the total energy transmitted is the same, but we're just doing it spread across a wider spectrum. Then at the receiving end, we do the opposite process, despreading. So we concentrate all that energy back into the original narrowband. Now, the reason this is very effective is that our channel distortions are frequency dependent. So I talked earlier about frequency selective fading. And this is a simple example of what a channel might look like if there are two interfering paths. And here we're seeing constructive interference between the two paths. Here we're seeing destructive interference where they're cancelling each other out. Now, if we were to take our narrowband signal and place it somewhere in this spectrum, it's actually a bit of a lottery as to whether it gets through well or not. So if we're lucky, we're on here and we'll get good transmission. If we're unlucky, we'll be here and we'll get poor transmission. So the spread spectrum approach spreads our energy across a broad band. I always liken this to spread betting. It's instead of putting all your money on one horse, you're putting your money on a lot of horses. And so when we reconstruct at the receiving end, what we're getting is the average signal to noise ratio across the whole bandwidth. And that results in a much more robust system overall, much more reliable. Because as I said earlier, we can't measure or predict exactly where these nulls will be. And if we do measure them, they might change 100 milliseconds later. They might be completely different in a typical underwater channel. As well as that, our acoustic noise spectrum might be non-uniform. So we might have particular frequencies where there's high noise levels. And again, a narrowband signal, if it was sat on here, would perform poorly. The spread spectrum approach also hedges our bets from the point of view of the noise spectrum. So this is a very simple qualitative way of describing how spread spectrum transmission works. So how do we achieve spread spectrum signals? Well, one technique that are used in quite a lot of products we've developed in the past are what we call linear FM or chirp signals. So this is sweeping a frequency across a broad band. And this lends itself to a very simple implementation in the receiver called a match filter. So we have a filter that's tuned to the particular frequency sweep. And this makes us highly multipath and Doppler tolerant. So chirps also have nice Doppler tolerant properties. And this has been deployed in a lot of modems that are operating reliably out in the field. So the simplest way to send data via chirps is to have an up chirp sweeping from a minimum to a maximum frequency, and a down chirp going from a maximum to a minimum frequency. And that way we can use these two chirp waveforms to represent a binary 1 or a 0, and that allows us to send our digital data. So as I said, that's a very simple and very robust technique that works well if you don't want a high data rate. The downside is you've got pretty poor bandwidth utilization. So typically for a bandwidth of 8 kilohertz, we can reliably send data up to about 100 bits per second with this technique. Another downside to it, depending on the application, is that chirp signals are very easily detected against the background. Now, in some applications, that doesn't matter, but in, for example, defense applications where we don't want our signals to be heard easily, chirp signals are generally a bad idea. The other thing is, from a point of view of trying to minimize impact on marine life, chirp signals stand out very clearly against the background noise. And this is not a coincidence. This is the reason that dolphins and whales typically use chirp signals for their vocalizations, for their communication. So in some respects, as I said earlier, chirps are kind of an idea we borrowed from nature. Another way of achieving spread spectrum transmission is using pseudo-random signals, which are much more noise-like in nature. And a technique that we work on a lot in our recent product developments is what we call emery orthogonal signaling. And the idea here is that we have a family of pseudo-random signals, which are generated from what we call binary shift register sequences. And if we have a family of these and they're poorly correlated or ideally perfectly orthogonal, we can send our data, and if we've got a large family of these, we can send a lot of data with each single sequence that we transmit. So for example, we might have 16 different pseudo-random signals, and with that we can transmit 4 bits of information, 2 to the power of 4 permutations. If we've got 256 available codes or signals, then we can send 8 bits of information. So we're developing products and research-based systems that are using between 16 and 256 orthogonal codes as our signaling set. And this is vastly superior to other potential spread spectrum techniques like what we call direct sequence spread spectrum. We're essentially just using a spreading gain superimposed on a phase modulated or quadrature amplitude modulated system. So this is very efficient when we've got a long pseudo-random sequence, and what we call our BT product, or bandwidth time product, is high. And you'll see in this simulation here how as we increase the number of codes and hence increase our data rate, we actually only have a small penalty in performance. Whereas with the QAM-based systems, we have a big penalty in performance each time we increase the data rate. So this is a plot of bit error rate against signal to noise ratio. And so this constitutes good performance, this constitutes poorer performance, because we have to have a higher signal to noise ratio for a given bit error probability. But a other big advantage of this is that we have a noise-like signature, and for some applications, a noise-like signature that blends into the background is very desirable. So I'm going to talk about a few examples of our recent research projects. This is the biggest project we're working on at the moment, and it's actually been extended from the dates shown here, largely due to COVID, I might add. But USmart is a project about underwater wireless sensor networks and the underwater Internet of Things, as I described earlier. So our goal here is to try and demonstrate a step change in the cost effectiveness of subsea data gathering. So we're talking about networks of small, low cost, low power devices that are making measurements, sending their data through the water using efficient transmission schemes, multi-hopping their data between different devices, and ultimately getting to a gateway buoy on the surface to transfer data back to the user on shore. And the applications here are looking at environmental monitoring, monitoring subsea assets, and even potentially monitoring biodiversity, as I'll show later on. So this is a collaboration between Newcastle University, Heriot-Watt University in Scotland, and the University of York, who are about 100 miles south of Newcastle. For those of you who don't know, Newcastle is the most northerly city in England. So if you keep going north of Newcastle, eventually you're in Scotland. So the big building block for the USmart project has been the nanomodem technology. Now, our colleagues at University of Washington have been using some previous generation of this technology. What I'm going to talk about now are the version 3, the V3 nanomodem, which has been enhanced in terms of data rate and protocols and so on. So the concept of the nanomodem was to produce a very small circuit and also a very low cost circuit. And we've used a lot of optimizations and cost engineering to get this device down both in size, cost, and indeed power consumption. So here we're talking about a circuit measuring 45 millimeters by 27 millimeters. We put that together with a very small piezoelectric transducer, which transmits and receives the sound. And this circuit actually sits inside the transducer, and we can encapsulate the whole thing in polyurethane to make it waterproof. Everything on this board has been chosen to be pressure tolerant, so it can achieve quite significant depth rating with this design, accepting that the pressure from outside is actually going to be transferred to the components on the board. But if we encapsulate well and we fill all the voids, then we have a very robust design that's well waterproofed and quite pressure tolerant. And it's a low cost construction compared to building a metal pressure housing with seals and so on. So the total assembly, once it's encapsulated, measures about 40 millimeters by 60 millimeters. This is the architecture of this circuit. So it's all based around an ARM microprocessor. So ARMs are pretty much in most consumer products we use nowadays. So certainly all our mobile phones are based around ARM processors. And the Cortex M0 is a very low-end version of that processor aimed at low-power applications. But that gives us the signal processing engine for both transmitting and receiving our signals. And we put this together with highly cost engineered circuits for the transmit circuit that drives the transmitting transducer, and the receiving circuit that amplifies the signals that come in from the distance. This is put together through a bandpass filter to eliminate out of band noise, and then it's fed into the microprocessor via analog to digital converters. So this is our basic architecture for the nanomodem. And as I said, every component in this has been chosen very carefully for minimum cost and also minimum power consumption. So typically this device would be interfaced to either a PC or some other embedded platform via a serial communication link using just simple RS-232 protocol. This is a specification of the V3 modem that we've developed in the USmart project. So it operates typically from a 5 or 6 volt supply, which means we can run it from typically 4 alkaline cells, like AA cells or larger cells if we've got room. It has very low power supply consumption. So supply current from a 5 volt supply is about 2 milliamps listening. So that's about 10 milliwatts power consumption when it's listening for signals. When it's receiving a message, that goes up to about 4 milliamps. And when it's transmitting, that's about 250 milliamps. So it's about 1.5 watts transmitting power, which is relatively low for an acoustic communication link that can send distances of 2 kilometers in seawater. So these low receiving power consumptions are critical to allow us to operate the devices for long periods in the field from a relatively small battery pack. And so we can run them for months and months or even years from relatively small battery packs. Our acoustic signal level is relatively low. So this is a source power level of 168 dB. So this is less than 1 watt of energy going into the water acoustically. And as I said, by most underwater communication system standards, this is pretty low. And we've done this deliberately because we want these devices to be biologically friendly. We don't want to create a big problem with anthropogenic noise. And so if we're going to have large networks of systems operating out there, we want to limit our source level and avoid causing a problem with noise pollution. And I'll say a bit more about that later. So our data rate on the V3 modem is 640 bits per second. The V2 modem that Washington have been working with in previous years only has a bit rate of 40 bits per second. So this is quite a substantial increase on what was previously available. And this can send messages to all nodes, i.e. a broadcast, or it can send messages to a particular node, i.e. what we call unicast, with packets up to 64 bytes. We can address a large number of nodes up to 255. Like the C-track that I described earlier, it can measure range very accurately with an increment of 5 centimeters and a typical variance of about 10 centimeters. And this maximum range, and this is based on extensive trials by us and also other customers who've used the technology, it'll do 2 kilometers in seawater, and this has been tested in a few different environments like the North Sea and the Mediterranean. And in fresh water, due to the lower attenuation, we've actually successfully tested at ranges up to 4 kilometers. So this was in Loch Ness, for example. And a key factor is the low cost of production. So we've got the production of these nanomodem PCBs down to about $19 in quantities of 500, which means we can make very affordable devices. And obviously a commercial product's never going to be this cheap. We've got to have overheads and realistic markups on a commercial product. But this low cost of assembly enables ultimately a lower cost when it hits the market. And just to illustrate the energy budget, from 4 AA cells, these are standard alkaline AA cells like Duracells, a device can listen for 60 days. It could transfer 2 megabytes of data or do 300,000 positioning pings. These are short messages that we use for ranging if we're doing navigation. And we're actually already started working on a version 4 targeting about 1 milliwatt of receive power to increase our life by about a factor of 10. How do we achieve this? Well, we achieve this, just check where we are for time. Yeah, we achieve this by what we call sparse signal processing. So we're using tricks to simplify the signal processing from the textbook approach, which would involve a lot of computation, and reducing the number of instructions per second required by the processor. So first trick we use is what we call bandpass sampling or subsampling. So instead of sampling at several times the highest frequency present, we allow aliasing to occur in the sampling process. So we're sort of bending Nyquist's theorem on sampling to allow us to sample at a much lower rate, but we're doing this by controlling the aliasing. So our signals are sampled at a particular frequency, which means the effect of aliasing is to reflect them down to a band between 0 and the actual bandwidth, where we can process it at a much lower sampling rate. And this reduces the number of computations we have to do. The other thing we do is we simplify the arithmetic. So in some cases, our correlation processing, we can reduce one of the coefficients down to a single bit representation. So for example, instead of doing a 16-bit by a 16-bit multiplication, we only have to do a 1-bit by a 16-bit multiplication. And in fact, that's actually just an addition or a subtraction. And in some cases, we even hard limit our signals after they've been filtered sufficiently. And we can do single bit arithmetic. So we can do one by 1-bit convolution. And this can be done very efficiently with digital hardware. So these are the sort of tricks we play to reduce the complexity of the receiver implementation and hence reduce the power consumption. So it can greatly reduce the clock frequency and the sampling rate on our hardware. And that's what allows us to receive signals with milliwatts of processing power. In terms of what does this cost us in performance? Well, these three plots here show us examples of cross correlations of our signals. These are cross correlations of pseudo-random sequences. And with the full precision and full sampling rate, this is what we see. With subsampling and 1-bit arithmetic, this is what we see. And we can see here that the background on this correlation, this is what we call the correlation side lobes, has increased. However, in a typical application, our background noise level would be somewhere around here between 0.2 and 3. So actually these side lobe levels are negligible compared to the channel noise. And so we can get away with a great increase, a huge decrease in computational load, and we've only sacrificed a small amount of signal performance. And actually the hard limiting approach only starts to affect us severely when our signal to noise ratio gets down to about 0 dBs, where we've got as much noise as signal. So if our signal's buried below the noise, we can't tend to use this approach, but in most practical applications, our signal to noise ratio is somewhere above 0 dBs. And this has quite small effect on our communication performance. So these are the sort of tricks we play in making these devices cheaper. So this is a simulation of overall modem performance for the V3. This is showing probability of a packet error. So here 10 to the minus 3 means 1 in 1,000 packets would be lost. And this is signal to noise ratio. And what we see is in a channel with no multipath effects, this is our performance curve, and we can actually receive packets below 0 dB signal to noise ratio when there's more noise than signal. As we start to add multipath, the effect of multipath in this system is effectively just to degrade SNR, so the curves shift to the right. This is because the pseudo-random signals that we've designed, they transform multipath into uncorrelated noise. So multipath interference just appears to have the same effect as uncorrelated noise. And this is quite a nice property, and it's also independent of what the delay is on the multipath. So it can be 1 millisecond or 100 millisecond, and it has the same effect in terms of this additive noise. So in terms of what we do to test out in Newcastle and off the coast here, we have a test bed about 3 kilometers from shore. This is wirelessly linked back to a building which belongs to the university. So this is the marine station where our research vessel is moored. And this buoy here is solar powered. It's anchored permanently. It has a high-speed Wi-Fi link 3 kilometers back to shore. And this allows us to put our modems underneath. We also have hydrophones on here permanently streaming back signals so it can monitor what's happening out there. And everything's fed back via Wi-Fi. And then once we're on the university network, everything's fed back to the campus in Newcastle. And we can sit and look at our data flowing through. We can even run software-defined receivers for our communication signals by processing the hydrophone streams in real time, because they're streamed through to Newcastle. And actually, we've got a YouTube channel where you can listen in on the hydrophone signals. Unfortunately, that's down at the moment, but we should have that back up early next year. So here, these are examples where we've put small networks of underwater sensors out there. So here we've got our data buoy. Here we've got a few wireless sensors which are equipped with nanomodems. So these are completely self-contained battery-powered devices. They're measuring data and sending back to the data buoy, then the data buoy back to shore. And down the right-hand side here, showing packet delivery performance over a period of about a month, although we've got 6 months worth of data here. This is just showing a 1 month period that we analyzed in detail. So here we've got packet success rate, which is near 100% most of the time. We've got a few periods where it's dropping down. So this is the probability of any one packet of data being received and transferred through to the gateway. Once we introduce our protocol, which allows for some retries if we have an unsuccessful packet transmission, so we have acknowledgement of the data and then a retransmission if necessary, then with a maximum of 3 retries, then we get to pretty much 100% delivery of our sensor data across the whole period. There's only a couple of instances where we didn't get our data through. So this is thousands of updates. These devices are sending once an hour, they're sending an update from all of their sensors. And this is thousands of updates over this period. And there's only a handful that we weren't able to get through. These periods here are where due to IT issues, the gateway was unavailable. So we couldn't actually send data even if we wanted to. So this is a case where we've demonstrated over quite a long period the robustness of the communications and also the robustness of the electronic devices. And this technology demonstrated a 6-month deployment using 2D cells for the battery pack in each of these sensors. We can also use our devices for tracking. So this is an example of us tracking an AUV. So we've got one modem on the vehicle, and we're tracking it as it's completing what we call a lawnmower search pattern. We can also use these in a GPS-like fashion. So we can have beacons on the surface that periodically transmit messages. And by receiving these messages, an underwater device is able to calculate its own position. So this is very like GPS. We can have any number of devices under the water, and just by listening, they can work out their own position. So here's an example where we took an autonomous vehicle through our network. The blue trace is the actual track of the vehicle. The pink dots are our estimations from the underwater GPS system. So here you see very good agreement. So finally, I'm just going to talk about a couple of examples of our sensor payload. So I'm conscious that we're almost running out of time. So the first one is marine mammal monitoring, where we're using similar devices to listen for echolocation click trains from the dolphins. And whenever they detect dolphins, they're actually sending that information through to the gateway. So we get pretty much real-time updates on animal movements in the area. So we do this by detecting and classifying the click trains. We know from lots of research that the frequency and time domain characteristics of the waveforms from different species can allow us to identify whether we've got a dolphin, whether we've got a porpoise, and so on. The other thing we need to do is eliminate common man-made sources like sonars. But our real challenge here is how we do this in real time with low energy. And probably don't have time to go into this now, but essentially we use a combination of low power detection techniques, which have quite high false alarm rates. But whenever we trigger on the low power mode, we wake up some more energy intensive digital processing where we can more accurately classify the signal and decide with a high degree of accuracy whether it's the signals we're looking for, whether it's a dolphin, a porpoise, whether it's a sonar, and we ignore it in that case. And then only then, if it passes all of these more sophisticated signal processing tests, do we transmit the data through our acoustic network. And this is what the so-called nanopalm devices look like. So this is our nano modem. This is the transducer that's listening for dolphins and porpoises. And this is the circuit that's classifying the echolocation click trains. These are the batteries you can see here. And so we've had some very promising results with very high, or rather very low false positive rates. We've managed to corroborate every detection of animals, either with sound trap recordings, or recordings of the signals nearby that have been manually analyzed to decide if there were dolphins or porpoises. And also most of our detections are also corroborated by local enthusiasts who are watching these dolphins all the time and post their sightings on social media as well. Another thing we've been doing with the same kind of technology is detecting cavitation noise from vessels. So we can do similar types of low energy processing to detect the signatures of vessels, and again use our acoustic network to report back when we detect things. And this is proven quite an attractive proposition for things like detecting illegal vessel movement. So this could be people trafficking, for example, unlicensed fishing. And so there's a lot of interest from enforcement agencies and people monitoring and protecting the marine environment to try and pick up vessels that aren't carrying AIS transponders and don't show up well on radar, but we can detect them from quite a long range using our acoustic detection. So these are examples of where ships have come past and we've actually locked onto the blade frequency of the propeller, and we're able to detect that that's definitely a vessel, and if we've got AIS, we can identify what the vessel is. If we don't have an AIS, then we know it's an unknown vessel, which otherwise wouldn't have been detected in the area. And interestingly, we managed to view the impact of the COVID-19 lockdown in the UK from an underwater network. So this is vessel detection rates prior to lockdown, after lockdown, when the fishing fleet and quite a lot of freight traffic completely died off, we observed far less detections from our system. So we even measured the impact from the bottom of the North Sea. Right, okay, because we're running out of time, I'll stop there, and thank you very much for listening, and I'm happy to hang around if anyone's got any questions.
Thanks so much, Jeff. That was awesome. I had a quick question. I know that on the V3 nanomodems, you are measuring the signal to noise ratio and monitoring that. And you mentioned that the side lobes on the sort of reduced algorithm process kind of prevent you from getting down into sort of the depths of when you have maybe more ambient noise than signal.
Yeah, that's less the case on the V3 modems. So we only use the binary arithmetic, the hard limited processing on the initial, what we call frame synchronization on the start of the waveform. The rest of the data is done in the intermediate mode, where we're still sampling the signal with 16-bit resolution. And from that, we can actually measure signal to noise ratio and absolute signal strength a lot more accurately.
Okay. I was going to ask if you switch off between the methods, and yes.
Yeah. So this is our lowest power mode. This is sort of our intermediate mode. And so the device spends most of its life in this mode and then switches to this mode when it detects the start of a packet.
Nice. Thanks.
Well, while people are still here, I'll probably just focus in on the very last slides, since it's quite interesting. We're often asked about the anthropogenic noise contribution from these acoustic modems. And as I said earlier, we transmit relatively low energy, and we're also transmitting noise-like signals that blend in very nicely with the background noise. And those two things do help to reduce the impact on marine life. And there are quite a lot of research papers out there where people have studied the impact of different signals and different signal levels. And so we've used a lot of that to inform the design of these devices. But this plot here is quite a nice way to illustrate this. So this is a spectrogram view of a hydrophone signal, and everything you see in the background here is from vessel noise. This is from a small survey vessel about 1 kilometer away from the hydrophone. And so what we can see is a lot of energy continuously across a very broad spectrum. Circles here is one of our acoustic modem transmissions in the midst of that. So we're talking about a lot less energy over a restricted bandwidth than for a very small duty cycle. And so one of the things I'm always keen to argue is that potentially using acoustic transmission networks like this to gather data instead of chugging around in survey boats is potentially going to reduce anthropogenic noise in the environment rather than increase it. If these devices are used in the right way with low duty cycle transmission, which they generally are, for example, our networks are sending a short burst of less than a second once per hour. So it was just a point I wanted to emphasize, because it's a question I'm quite commonly asked.
Do we have any other questions for Jeff? Okay, I'll just say we've speculated a number of times about exactly what the nanomodems are doing, and this was great to get a really in-depth dive into some of these spectral processes, the digital signal processing. So yeah, that was a lot of fun. Okay,
Good. Glad you enjoyed it.
Yeah, this is a good resource. Let's give.
Well, the even smaller version of the modem is pictured here. I didn't have time to get into this, but this is an even smaller version. This is aimed at tagging fishing nets. Okay. The idea being that lost fishing nets, ghost nets, could be easily located and recovered if they're equipped with a very low cost transponder. And so this is what we're working on in a European project called NetTag. So they are getting even smaller, and we're actually been working with a company in Italy developing something even smaller again. But I'm sworn to secrecy about the application for that.
That sounds very cool.
Okay, well, thank you everybody for listening. It's been a pleasure. And if anybody's got any questions they'd like to follow up on, sorry. I was just going to share my email address there. So if anyone's got any questions you'd like to follow up on, feel free to email me in the future.